Märt Möls, and I'm a statistician. And my experience with remote sensing data is quite limited. But anyway, I think that sometimes somebody from some other field might be maybe point out or highlight some things that otherwise might remain unnoticed or maybe not unnoticed, but unrecognized, or people don't tend to think about them. And sometimes it might be useful if one has a little bit of this type of side view to his or her problems. And first, some context about which we will talk. Well, quite often, as I understand, the approach or the problem is following. From one hand, you have some remote sensing data, for example, satellite images, and then, in addition to it, you have some ground-based measurements of some feature of interest that you actually want to predict. Will it be some kind of plant cover or something else? And in some places, you have made actually some measurements, and you know what is the value of your variable of interest in those points in some certain time moment. And then the idea what you want to achieve is based on these measurements and based on this satellite images or remote sensing data. You want to kind of predict what happens in those points from where you don't have any measurements at all. So you want to use some predictive statistical model or machine learning model or artificial intelligence to predict how this variable of interest would behave in those points. Those areas between these points from where you have some measurements. So you want to kind of acquire some kind of prediction for all areas based on these two data sources. And but in addition, or let's say for example, let's take one more concrete example. Maybe you might have lidar measurements, and you might have some ground-based information, for example, about the forest height in this region, and based on these two data sources, you might want to build a statistical model to predict the forest height. How can you predict the forest height based from the lidar measurements, and then you can predict basically the forest height for all places, or from where for which places you have these lidar measurements available. Well, but in addition to these predictions, often also some measure of accuracy is required. One often wishes to know how accurate these predictions are. And usually for statistical models, it's not a big problem. You can there are tools usually available, like predict command in R, for many models or many model types, and quite often there is some kind of option. For example, we can ask for prediction interval, and we will be shown how accurate our prediction in one case or in another case is. Well, however, and you could use, instead of statistical calculations, one can also use cross-validation type of approach, where you can kind of remove one data point for which you actually know is a true value from this model building during model building, and you can use it later to kind of see how accurately this data point is will be predicted by your model, and based on this information you can also acquire some kind of some measures of accuracy for your predictions. However, all these approaches, these statistical calculations usually, and these cross-validation type of approaches, assume that all these points are kind of in some sense of equal size. What do I mean is that ground-based measurement area is equal basically to the area for which you want to make the predictions. Or if you want to produce a map, for example, then basically you want to produce some pixels as your predictions that covers some certain area, and these usual calculations assume that these ground-based measurements have been made from areas of the same or similar size, at least in their default settings usually. However, people seldom understand that this measurement, this prediction accuracy depends quite a large bit on that. Depends on the area for which we want to acquire the prediction. And here is an example. We might have two areas of different size. And if we use the same model to predict the forest height for both types of areas, then actually the precision will be quite different. We have much larger standard errors or standard deviation for the prediction errors for smaller patches than for larger patches. So this is in case of the same model, same training data, just the area for which we want to make the predictions is different. Now, what does it mean in practice, or what might it mean in practice? Well, the point is that if your training data collection area is different than the area for which you want to make predictions, then this prediction accuracy you calculate from this from your training data does not adequately reflect the accuracy you will get if you make predictions for a larger area. And for typical statistical applications, this is not the problem, because usually if you predict what happens with people, well, you have your unit is kind of one person. You usually don't deal with 1.5 persons, or it is quite clearly defined. But in spatial applications, you might be interested in making predictions for different sized areas, and it actually has the effect how accurate your predictions are. You can, in some sense, get more accurate predictions for larger areas than for smaller areas. Well, it is actually something that would be totally new thing. You probably already know it in this sense that if you have some variability, how accurately you can predict one person, for example, or one observation, and if then somebody asks how accurately you can predict the mean of, let's say, 4 observations, then those very basic standard formulas states that the variability of your sample mean is standard deviation of one observation divided by square root of n, or divided by square root of your sample size. Here we have a sample of size 4, so square root of 4 is 2. So basically, if we would try to predict the mean of 4 people, then we can get much more accurate predictions compared to if we just want to predict the value of interest for one person. No, that's true. This formula holds only if we have independent observations. This classical formula for the standard error of the mean. But actually, it can be sometimes quite insight, even for those applications that use remote sensing data. For example, the previous example where we had different sized target areas. Some forest measurements have been done in circles with radius 10 meters, and some measurements have been collected from smaller areas from circles with radius 7 meters. And we already noticed that the prediction accuracy, how accurately we can predict the height for this type of circles and for this type of circles, it was different if we use the same model. Then we will get more accurate predictions for those larger areas. But if we start to look how these areas compare to each other, then in this case, basically, this area is the larger circle area is approximately 2 times larger than this smaller circle area. And if we so it's approximately 2 times larger sample size in some sense. So according to the simple formula for independent observations, errors would be approximately square root of 2 times smaller. And if I start to calculate it, if I take this standard deviation, if I divide it by the square root of 2, I get surprisingly similar result as we observed here. So, no, sometimes these simple formulas, even though they are not theoretically probably absolutely correct, but sometimes they can give some indication or starting point to understand what your precision might do if you change the area for which you want to make these predictions. Well, not always can we consider these prediction errors to be independent, or this formula would kind of indicate that if we take really small areas, let's say circles with radius 1 meter next to each other, those errors we make if we predict the forest height for one circle and the next circle, that these prediction errors would be independent to each other, then we could really rely on this type of calculations. But these errors are not always independent. Why they might not be independent? Well, there are some simple possible reasons. Now, for example, if your ground model is slightly wrong, if you kind of, for example, estimate weighs your ground wrongly in some area for whatever reason, because there is some special type of undergrowth in the forest present, or something like that, then probably these errors will be similar in one point and in the next point, that is maybe meter or two away from your first point. So in these situations, these mistakes or errors tend to be similar in larger areas, and in this case we really can't say that all these points in a circle or the smaller areas within these larger areas, that we can kind of consider them to be independent observations or independent entities. These errors, prediction errors in those smaller areas, start to be correlated, start to behave similarly, and in those cases, really, this simple formula for which allowed us to scale according to the sample size won't work in this context anymore. But technically, it's not really a stopping point, because in principle, I won't go into the details of this formula. It's just something I picked up from one of my lecture slides. But basically, it describes how to calculate the prediction error or mean square error for observations in case there is correlation between these measurement errors present. Details are not important here. Now, one thing, there are two things that I want you to kind of understand or think about. One thing is that in principle you can calculate even for correlated cases how large your errors will be for different sizes, different sized areas. However, one important thing is that you need some inputs for this formula, for these calculations. And basically, you need to know how are errors correlated to each other. Basically, how this prediction errors, correlation between prediction errors changes over the distance. If you start to modify the distance between points, how correlated, how strongly these prediction errors are correlated to each other, you need some kind of model to predict this correlation. Then you can apply those more complex formulas for calculations. You can describe this correlation between prediction errors in different ways. You can try to estimate a function describing correlation, how this correlation between prediction errors depends on distance, or you can maybe those people dealing with maps are more familiar with variograms or semi-variograms that present basically the same kind of information that is needed. So basically, as an input, you will need some kind of information about semi-variogram or information about how this correlation between prediction errors will change if the distance between points will change. Then you can still, even under correlated observation or under correlated prediction errors, calculate how accurate your predictions will be. However, there is a question that what do you need to estimate these semi-variograms or this type of graphs or this type of functions which describe how your correlation between prediction errors depend on distance. Well, basically, you need some observations available in different distances. Some ground observations, some ground measurements that have been made, something like 10 meters apart, 15 meters apart, 200 meters apart, and so on. So you could, and in some sets, in some different areas, so that you can kind of start to grasp or start to model how this correlation between your prediction errors start to vanish or disappear. And sometimes it turns out to be a problem, because I can quite understand, but the reasoning behind it also. But from this application point of view, if you have a really very nice grid, exact grid of points where you have made your ground measurements, each point exactly the same distance of from the next one, they are kind of spaced, so in some sense ideally that the distance between the points is always as maximal or as big as possible. In some sense, this kind of data is really bad or really difficult type of data to fit or to guess something about these curves, because you kind of don't have observations for large areas, or there will be large gaps You have to just guess how your correlation behaves. You don't have anything concrete or anything real measurements that you can use that you could use to fill in this curve or to guess how this curve might look like in these areas between